Okay, hello everyone. So today we're carrying on with combinatorics. Excuse my lack of enthusiasm. I'll introduce our instructors again with Jerry Dye. 11.5. It's actually like 11.8 by now, isn't it? Wait, that's like no, it's been half a year since you've done that, so it should be year 12.
I know. It works out somehow.
Okay, this is me, and this is our topic. Okay, so let's just get into it. So let's start off with our combinatorial games. Let's just start off with, I guess, describing what these are. So we have combinatorial games are games that satisfy these properties. It's basically just two players playing a turn-based game where there's like no luck. So it can be like the entire game can kind of be solved, I guess. Right. Something like tic-tac-toe or chess. Even though chess is like too complicated, too complex, right? Too many moves for us to actually fully solve, there is a solution, as in we can like determine like which player must win. I guess that kind of leads to like something called like the fundamental theorem of combinatorial games. And basically what it states is that for any combinatorial game, for any like two-player non-luck turn-based game, either one player like has a winning strategy or it's always going to end in a draw. So you're never going to have like, if both players play optimally, it's never going to be like player one wins sometimes and player two wins sometimes. It'll either be player one wins all the time or player two wins all of the time, or they draw like 100% of the time. And when we're dealing with combinatorial games, we basically always assume that both players are like playing optimally, right? So yeah, like we're assuming they're perfect like logicians and stuff. Okay, so like the way that we like solve a combinatorial game, or you prove one player can always win or they always draw, is you just show like you find a strategy, you describe a strategy for one of the players, right? Something like, oh, always take the larger number, or always take this amount of rocks from the thing, or whatever, blah blah blah. And you want to show that by following some strategy, player one or player two can always win the game. And yeah, uh, but maybe sometimes the game like isn't winnable for either player. In that case, what you need to prove is that like both players can't lose. Like I find a strategy for player one, that means that player one never loses. And then I find a strategy for player two, that means that player two never loses. And okay, well, if neither of them lose, then clearly it's just always a draw, right? So okay, let's just move on to our first like example. We have quite a few examples and exercises today, so might want to go a bit quick. Yeah. So here's our first example. Two players take turns placing dominoes, so like a 1x2 domino, on a 6x6 board without overlapping them. And the first player who can't place a domino loses. So we're asking, given optimal play from like both sides, like who must win? Yeah, I guess this is an example, so I'll just quickly go over like the strategy for this. So this uses like a pretty common tactic, like type of strategy in these games, which is it's based off like symmetry. So I mean, I'll just say the strategy, I guess, right? I won't give too much motivation for it, but just remember that this is like a very common strategy in these games. It's basically just mirroring your opponent, like using some kind of symmetry. So I guess if we go to the slides here, I'm not sure what Jerry's drawing here. So very, it's maybe this maybe you.
Nah, that's
Was
too
that,
far.
was that
Okay,
maybe a
okay.
soft pig toy? Okay,
So, okay, I'll tell you
Jerry, can you
guys the
drop the board?
strategy.
Thanks.
I got you. I got you.
Oh, that's good. So we
I
have our
got
six by
this.
six board here, and so okay, for example, right? What I mean by symmetry is, I guess, like if you take, so this is the center of the board, right? You can do this like a few different ways. I guess I'll just do like reflectional symmetry across the middle of the board. I think does that work? That works, right? No, it doesn't work. My bad. My bad. My bad.
No,
Um,
I think it's
yeah, it
rotational
has to be
symmetry.
rotational, so like 180 like degree rotational symmetry, right? So let's say player one places their domino here. Then um what like player two can do is they can like rotate this domino or rotate this spot on the square 180 degrees.
Wait,
Like if you
Chris, I
imagine like,
got you. I'll draw a different color. I'll use a different
oh,
color.
that's so smart. So if I'm black and I'm playing player one, then Jerry can mirror my spot and play there as red, right? So maybe then I can play here.
That's quite true.
And basically, notice that the reason the strategy works is that if me playing as black, if I can make a move, right? If I can make any move, then Jerry playing as red is always guaranteed to be able to make a move as well because because well, proof by looking at it. No,
No, it's sort of like a
yeah, Jerry, what's the proof?
wait. It's sort of like a bijection between the where you place your domino and where the other person places their domino. Because if you kind of think about pairing up all of the possible placements for all of the dominoes, like the domino here, the one that's paired to it is going to be the one that's rotated 180 degrees, which is here.
Yeah,
And
I guess
if
the
the other
important thing,
person places,
yeah, I guess the important thing is that when you have a domino, right? Like if I like when you have some kind of domino, like maybe something over here. Actually, so I'll just use a laser for this, right? Like if I have like a domino here and I rotate it over here, both the original domino and the rotated domino will never overlap with each other. That's the important part, right? So, like I guess what you can say is that like suppose for the sake of contradiction that I place my domino here, but Jerry can't rotate it 180 degrees. But the thing is, if he can't rotate 180 degrees, that means that either he played a domino there in some like previous turn, or I played a domino there in some previous turn. But that clearly can't be possible. Like if he had placed a domino here in some previous turn, then I would have placed it where he had just placed it, right? But if I had placed it here in some previous turn, that would have meant that like he would have placed it where he had just placed it, which isn't possible because
that's
you can't place
facts.
something
That's
somewhere
facts.
twice. Okay, my bad for the bad explanation, but hopefully you kind of get what I mean.
No,
Um,
like yeah, this is why the reflection strategy doesn't work because if you place a domino like here, right, then it crosses the line and you have to kind of do some extra tampering to get it to work.
yeah. So what Jerry's saying is that like you might try like this is the first strategy that I was just thinking of, right? If I draw like a simplified board here, um, I was like, okay, well, what if we just do a strategy where we reflect it across like this middle thing, right? So for example, if Jerry places, I place here, Jerry places here, right? That one doesn't work because if Jerry places in the middle, I can't reflect it and then place it here again. The reason the rotational strategy works is that wherever like is whenever you have a domino and you rotate it 180 degrees, the two won't overlap, which means that you'll always be able to find space to place your new domino, given your opponent had space to place their domino. Anyway, so but basically what that's saying is that if player one can make a move, player two can always make a move, which means that like player one eventually has to lose. They can't make a move, right? Because you can't go on like forever. Um, yeah, notice that like whenever you have this type of game where there is no draw available, right? Like this game eventually ends and one player eventually loses. This means that like one player like must have a winning strategy just by like the way that combinatorial games work, right? So it's not like you can't say neither player has a winning strategy. Some player definitely has one, and in this case, it must be player two by that like kind of symmetry like argument. Okay, I guess we can move on to like an exercise which or like a problem which uses like a pretty similar idea. Wait, Jay, did you look at these like problems beforehand?
No, it's fine. It's fine.
Okay, you can do it with the kids.
Wait, no, why is this just 2020? What?
Was it on wait, was it 2015?
Yeah, the one where you had like the
Yeah,
down.
no, yeah, I stole this off. No, yeah, I stole this off like a simplified 2015 C4.
Oh my god.
Nah, because I was like really struggling. I was trying to think of like commentary games last night. It was like 12 a.m.
You can just Google the problems. It's fine. Wait, so
Would you
are we
I'm gonna
gonna
like drop the
teach them?
grid? Hmm? That's a
Are
problem.
we gonna
Okay,
teach them like? No, no, no.
what
What
what are we
about like
teaching?
the the fundamental theorem of combinatorial games?
Did I not mention that? That's just like basically saying that like either
Yeah, but
one
like
player always
it's
wins
fine.
or they always draw.
No, but we should have made a slide on it to pad the runtime of the lesson.
Man, there's already enough slides. We have 19. Like this is like too long. It's okay. No, we have too many
No, but
exercises.
we
Okay,
have to.
let's move on to like explain this one. Okay.
No, bro. No.
Okay, so we have a 1 by 10 grid here, right? So okay, it's Chris and Jerry. That's me and Jerry. So does anyone have like any ideas on how you might use like principle we learned just then to like make some progress on this question, maybe? Okay, so Jackie, yeah, split in half and try to reflect. Okay, yeah, that's great, right? So we're gonna try to use the same reflection principle. And this time you can't like, well, not reflection, the symmetry principle, right? So this time you can't like rotate because it's just 1 by thing, right? So maybe we just try the yo, wait, what's going on? Why is okay, this
Okay,
Jamble's like not letting me
technically the
speak.
reflection is also a rotation. You know,
Oh, wait,
technically.
oh, that's right, that's right. Okay, anyway, sorry. Yeah. So okay, I see some pretty good ideas. So let's try to split it down the middle. So this is why it's important we have a 1 by 2 in grid, right? We can split into one, a five, and then a 1 by 5, and then another 1 by 5. So the basic idea, I guess, is that so I never I guess I start, right? Wait, why did you draw another grid?
No,
So
because
if
David said something, right? We want to explore his idea as well.
oh wait, what did I thought David said the same thing as like okay, yeah, we can have a look at
No,
that
he
later.
said to pair up the squares. I think that works, right? Wait, does
Okay,
it?
let's have a look at wait, we can have a look at that later. Okay, so I guess like this is like the like what the solution I had intended. So it's every time that I play somewhere, Jerry just plays on the like opposite side that's like well, on the reflected side, like on the corresponding square, but like reflected across the middle like axis. So okay, this is a pretty simple strategy, but like with every strategy in these games, you kind of have to prove why it works, right? Um, so okay, the reason it works is first of all, every time I place a C somewhere, there will always be a space on the other side, on the corresponding side, for J to place a J. And the reason is because, I mean, it's similar to the last question where it's like, if there wasn't a space there, either I placed one, which means that like the space that I had just placed in wouldn't have been available, or J placed one, in which case, okay, it just doesn't work, right? It's like, because like you always like get rid of squares in pairs. It's like this square and this square, you get rid of them at the same time. Then this one and this one, you get rid of them at the same time, right? Like I place one, J places in the other. I place in one, J places in the other. So it's not like you're ever gonna. It's not like there's ever gonna be um a move where I place in some square and then Jerry can't place in the other. So like
Quite true.
Jerry, so there'll always be a free square for Jerry to place in, but you have to satisfy the other condition as well, which is like you can't place a C next to another C and you can't place a J next to another J, right? So if I can make a move, i.e., my C is not next to a C, then we have to show that Jerry's J is not next to another J. Um, but I think okay, so David says his strategy doesn't work. Okay, that's unfortunate, but yeah, that's good that you found like that it didn't work, right? Not fake solve. So um, I think you can just. I mean, it's just wait, Jay, okay, can I just say like by symmetry? What's it, J, okay, that's fine.
You probably could, right?
Yeah, like it's just by symmetry, right? Because like the C's and the J's, okay, it's like if you reflected the entire board about this entire thing, like every C turns into a like J, and every J like turns into a C, right? So it's like if Jerry places a J and it's next to another J, that would have meant my C was next to another C first, which would have been bad. So if I can place my C in a valid square, Jerry can reflect it across this middle axis, and he can place his J in a valid like square as well. Which again is following the same principle where if I can make a move, we've shown that Jerry can make a move, which means that like Jerry will never be the last one who can make a wait, Jerry will never be the one who can't make a move first. right? It'll always be me. It's like I can make a move, then Jerry can make a move by reflecting my move. So then I'm always the one who's like keep trying to find like new valid moves to make, and eventually I'm gonna not be able to find a move to make, and at that point I lose, right? So
Quite
again,
true.
by the same like kind of like reflectional like strategy or like symmetry strategy, player two can like yeah can just like hold out and eventually player one can't make a move, and then yeah, cool. Okay, next one. I think it was some like mind your decisions video I saw. You know, I think it's just a classic like common game anyway. Okay, maybe I should like describe. Okay, I hope everyone knows how like a knight moves. It's like you move two in one direction and then you move one in like an orthogonal direction. So it's like an L shape. Okay, so again, um, actually this question is like not. Wait. Okay, this question is a bit misleading. This question is not like the same symmetry argument. This one's more like a pairing argument, I guess. Well, you can kind of think of this. So what I mean by a pairing argument is you can kind of think of our strategy here as a pairing argument as well, right? Where like this square is paired with this square is paired with this square. And it's basically saying if I play in one of the squares, right, then Jerry will play in the corresponding square that's paired with. So that's what I mean by like a pairing argument. It's like if you place in that square, I'll place in this like in the paired square, right, in the corresponding paired square. And yeah, so for this question, maybe try find like a way of pairing squares such that like yeah, such that if they play in a square, you can play in your corresponding square. Jerry, I'm gonna be like writing up like summaries of what we're doing.
Oh, that's true. I do.
Yeah,
But
probably should. But if
how
you think
about you
about it,
do
it's only like
that?
5 participants anyway. So okay, well, I'll just give an example of like what I mean. So it's like um maybe I'll pair this square with this square. So if Alice moves here ever, well, if Alice like starts here, right? Then or if like let's say Alice moves here, then Bob like moves to the corresponding square that's paired with. Like if Alice starts here, then Bob will go down here. And then yeah, like just keep pairing squares like this, I guess. And try like tile the entire board. Oh, also I totally forgot to send the jam. Okay, I'm sorry guys. I think it's like probably like third time it's happened. But first, sorry, I'll send the Jamboard link in here. I'll send the slides in here as well in case I don't know if this gets emailed to you guys. Probably does, but yeah. So you guys can have, like freely have a look at what's going on without needing to look at my screen. Okay. Like, does anyone have any ideas? Like any thoughts? Maybe I explained a bit badly. I think I did, but oh well. Okay, that's okay. Uh oh okay. That was just Jerry. Okay, that's fine. I'll just go over the solution, I guess. So we can continue pairing squares like this. It's like kind of you want to like tile the board with these like knight move like pairings. Okay, so here we've tiled like a complete 2x4 rectangle with these knight move pairings, right? And you can kind of extend this tiling throughout the entire board, right? I'll just do it a little bit more, but I think it's pretty easy to see that this like tiling just generalizes because a 2 by 4 rectangle, like you can just like copy paste this until it fills the entire 8 by 8 board. Um, maybe okay. I think more colors would have been better, but okay. So like, imagine we like
You can label the colors.
what?
Surely you can just label the colors like blue one,
Oh,
blue two. You know.
yeah. I mean, I'll see. I'm just like splitting up like this, right? Like,
Sure.
yeah. So we like split them into like distinct like 2 by 4 like sections like this, and in each like section you have this kind of pairing where blue hair pairs with blue hair, red hair pairs with red, yellow, green, green, right? So it's like if Alice places, let's say Alice starts by placing her knight on the yellow one, right? Then Bob just moves it to the corresponding color. So moves from here down to here. And then okay, Alice can move it to wherever she wants. Maybe she moves it to this green, to like green two. But then Bob has a corresponding green two to move it to, right? And wherever Alice moves it, she must move it. She must like move it into a new pair, right? Like because every time that Alice moves into a pair and Bob moves it to a corresponding pair, this yellow one pair, is kind of used up, right? Alice will never be able to move back into it again because the knight can't return to a square it's already visited. So like if Alice starts in this yellow one and Bob moves to this yellow one, then this yellow one pair is moved up, and now it's like kind of on Alice to go find a new pair. So maybe she finds this green two pair, then Bob can use this one up as well. And every time Alice has to go find a new pair over and over, but Bob can always just like move to the corresponding square as part of the pair. So he'll always be able to find a new like he'll always be able to find a move, right? A new square that he hasn't been to. So like they kind of just keep like you know like going or yeah, I mean, so again, it's kind of the same principle where given that Alice can make a move, Bob can also make a move, except this one's not really based on symmetry. It's based on like pairing up squares or like moves, which to show that like if Alice can make a move, Bob can also make a move. And it's kind of on, yeah, it's on Alice to make a move. So to find a move eventually, right? Like because there's only a finite number of moves that you can make, right? There's only 64 squares on the chessboard, and you can't visit any square more than once. Someone's gonna run out of like moves, and it's not gonna be Bob because like if Alice can make a move, Bob can make a move, right? So I think all three examples we've done here have kind of been this like same idea of like if player one can make a move, player two can make a move, therefore player two wins. But that's definitely not like all or even what most that's definitely not what all the combinatorics games are like, right? We'll show some examples where player one wins later. But I think just for now, I think a good portion of combinatorial games, like especially like easier ones, I'd kind of just like this, right? Where it's like you show for player two, okay, if player one can make a move, player two can make a move, and then therefore player two must always be able to make a move, and then they win.
Wait,
Yeah,
are
so
you
this is
going to
like,
talk about like
hmm?
the existence versus construction sort of thing? Like these problems are existence problems because I think it's like you just say if player one can make a move, then player two can make a move. But for some of the other constructive problems, it's like, well, if player two does this, then player one does this, and at
Oh,
the
that's
end,
true, that's
player
true. Yeah,
one
we're
wins
not
by
really outlining
default.
like an actual strategy. I mean, well, it's kind of like a strategy, I guess. Is this not a strategy though? Like, it's like given they move
No, but
to
all
any of these
combinatorial
squares, we move
games
to
have
corresponding square.
strategy,
What?
right?
Hmm?
Like the main like all combinatorial games have strategies, but the main difference is like I suppose how in depth those strategies are.
Sure.
Like this one, yeah.
No, but like I think what I mean by strategy is that like if I was playing this game against you as Bob, I would actually be able to win, right? Like I would know exactly what to do.
Yeah.
Later on, we get to some like real non-constructive proofs where it's like I can tell you that player one wins, but if I was playing player one, I genuinely would not know what to do like to win.
Oh, that's fair enough. Then
Like this game, like this
this
example later
this one
on,
is
it's like
construction. Yeah.
I mean like yeah. So this one's not okay. Whatever. I don't think that matters so much. It's fine. Okay. Anyway,
No, it's just
yeah.
the
Anyway, those are pretty
sequence.
cool, right? So it's like symmetry is very good, and like pairing up moves is like very good. Okay, cool. Let's move on to our second like chapter here, positional analysis. So positional analysis is kind of like if I gave you a position in chess, right? Like, well, maybe you wouldn't be able to say if it's winning or losing, right? But let's say if it was like really obvious, like if it's checkmate in like a one or checkmate in two or something, you would be able to say that is a winning position for you. It's winning because you can force a win from it, right? A losing position on the other hand is like, I mean, I'm just going to define it as like, if you're given this position, it's your turn, and you're looking at this position, and you have to make a move. It's losing if like you can't make any moves like to win the game, right? So like every position, well, in a game where like there's no draws, every position is either winning or losing. And like the idea of positional analysis is to kind of like start from the end. So the end position, like it's pretty easy to like figure out if it's winning or losing, right? Because there's not much to calculate. Like there's just like a few moves you can make, and you kind of work backwards from there. And you work backwards, like seeing if positions are winning or losing, and until you get to the starting position. And once you get there, you can figure out if the starting position is winning or losing for the first player or for the second player or whoever. Um, yeah, this doesn't work for like, I mean, this works for like simple games where you can actually analyze it, right? Like sometimes for like more complicated games, you're not gonna be able to like do this positional analysis because there's like too many moves to make and whatever. So this is like a pretty classic example. It's like the game of 21, right? So you have 21 coins, and I feel like on each turn, each player takes one, two, or three coins. I think this one, yeah, like maybe you guys have seen this one before. Um,
I swear we taught this last year.
yeah, we probably did. I think this is the only repeat. Yeah, whatever. I don't know. It's just like you got to start with this, right? Okay, maybe you don't have to start with this, but yeah, okay. So Jackie already knows. Okay, it's okay. Yeah, okay. So I guess we'll go through the example. So I'll call like the state of the game, like how many, wait, like number of coins. So when I say number of coins up here, I mean like this kind of like dictates like oh wait, I was doing like this. I'm gonna do it
Oh,
my way. Get out. Something
your
like this,
way or
right?
the highway.
So um so the state of a game is either winning or losing, right? So when I say number of coins, I mean like this is the number of coins you see in front of you at this moment, and it's your turn to play, right? So if you see zero coins in front of you, right, that means that like your opponent just took all the coins, which is like a good thing because if you're taking all the coins, you lose, right? So if you see zero coins in front of you, that's a win for you. If you see like if in front of you you see one coin and it's your turn, well you must pick up that coin, right? And therefore you lose. So this is kind of what I mean when I say like positions near the end of the game are easier to analyze, right? There's like not many things you can do. If there's two coins, well, you can either take two coins or take one coin, right? Obviously, if you take two coins, you're stupid. You lost the game, right? So you would rather like just take one coin and make your opponent lose. Again, if it's three coins left, you can just take two coins and send your opponent to a losing position, which is good. Right? Same with four coins. So you want to try send the game into a losing position. Like that's ultimately what you want to do, right? But notice here, if there's like five coins left on the table, you can either take away one coin. Um, so you can take away one coin, or you can take away two coins, or you take away three coins. But in all three of those like moves, you're sending it to another winning position, right? Where after you make that move, your opponent can just send it to one coin and then you lose. So we see that five coins is actually losing position. In general, what makes a position winning is if you can send it to a losing position. If you can send a position to a losing position, you must be winning because you can give your opponent a loss. But if you can only send it to winning positions, then it must be a losing position because you're forced to give your like opponent a win, right? So like, okay, well, maybe I'll just type it up here. Oops, my bad. Apostrophe. Yeah, so this is like kind of the basic idea, right? If you can give them a losing position, it's winning for you. If you can't give them a losing position, well, it must be losing for you, right? Oh wait, did I say we're losing? I meant winning. Whatever. Hopefully, yeah. Hopefully that's kind of clear. So if you just keep extending this pattern, right, until maybe you notice something, yeah, you notice that for the next three things, it's a win because you can always send it to a loss. But then for the next one, for nine, it's a loss because you can't send it to another loss. You have to give your opponent a win. So it goes like win, lose, win, 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 lose, win, 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 lose. And yeah, maybe you notice that um like for one mod four, it's a losing position, right? 1, 5, 9. And if you look at our original question, it starts with 21 um points. So 21 is one mod four. So 21 starts with a loss, which means that when the first player is presented with 21 coins and it's their turn to move, it's actually a loss for them. So okay, now the question is like, how do you write up this proof, right? So even though we looked at like small cases to kind of like figure out the winning and losing positions. I mean, you can write this up in your proof, and that's fine, but like you don't necessarily need to because the easiest like well once you figure out the winning and losing positions, the next thing to do is like actually figure out like what the strategy is for the winning player, right? I mean, the strategy for the winning player is just keep it at like one mod four. So yeah, you can which is like always possible because um if you're if you are already at a position that is one mod four, well, then you're forced to make it into a position that is not one mod four. So, like, if you're writing this up and you want to describe like an explicit strategy for the second player, then the strategy is just like like take a number of coins between 1 and 3, such that the remaining number of coins is one mod four. And you can always do this. It's not too hard to show. And once you do this, eventually you must leave your opponent with one coin, which is one mod four. And then they have to take that and then they lose. So like I guess like an example of like actually playing the game is like maybe, 21, then the first player takes like 3 coins, leaves at 18. And you want it to be one mod four. So, you as the second player will make it 17. And then maybe they take away one coin, but then now you can make it 13, like one mod four, right? So this is an example of like looking at like the state, the win-loss state of positions to figure out which positions are winning, which ones are losing, and then using that to try find a general strategy. Okay. Yeah, and eventually you give your opponent a 1, and then they take that, and then you win. Okay, cool. Let's look at the first of the two problems we have here. What is this? Okay, a two-player game is played on a 5x5 grid. Oh, wait, JD, you want to draw that up? Draw that up on like page 4.
Okay, I got you.
Okay, so like we start with a token in the bottom left, and basically what you can do is you can either like move the token a little bit, like 1 or 2 to the right, or you can move it to the like the next. You can like advance it a level to the next row. Yeah, so like it's kind of you start with the token here, and you can like move it 1 or move it 2, or you can like just skip the row and like teleport it like to the next row, right? Where if you reach the end of the row, then clearly your only move is to move it to the top of the next row. And was it the player who gets to the end loses? Yeah, okay. So wait, no, the player who can't make a
Yeah.
move loses.
Yeah, so like the one who is at the top.
Yeah, you win. Like if you reach here, you win, right?
Yeah.
Because then your opponent can't make a move anymore. Wait, what did I just do? Did I just delete the
I think you deleted the.
Wait, was that me who just
I'll
deleted
read
that?
what it did. Yikes.
My bad. Okay. Well, I mean, I guess no. Okay. So try to figure out like which of these squares are like a losing position. Okay, I'll start us off, I guess, right? So
Oh, I
um,
drew it so much better
the
this
top
time.
right is a loss. This position's a loss because what I mean by this position's a loss is if if the counter is on this square and it's your turn, then you've clearly lost because you can't make a move anymore, right? But like these positions, these two are wins because you can move it to the end and give your opponent no more squares. In other words, you can move it into a losing position, therefore it's a win. Whoa, Jerry, no spoiling, bro. What is wrong?
Hmm?
So yeah, maybe you can if you can try like follow this well like complete the square, right? Complete the entire square, and then you'll see if the initial square is a win or a loss. Remember that like if you can move it into a losing position, it's a win. But if you can't move it into a losing position, then it's a loss. Okay. Does someone like say like what the rest of this first row is if they didn't see Jerry's spoiler already?
What do you mean? It's fine.
Okay, so cool, Jackie got it. Does anyone else like want to try? Have a go? No? Okay, that's fine. Um, is that fine? That's not really that fine. I feel like, come on, guys. It's a 1 in 4 chance, right? Um, like there's like 4 people left. If you guys just all say one of the 4 each, then one person's gonna get it correct.
Wait, where did the other two people go?
Wait, never mind. There's only 4 people. Okay, don't worry. If the
What?
remaining 3 who's not
Oh,
Jackie guess, then that's like a 3 in 4 chance you guys get it correct.
this is so sad.
That's about unfortunate. Um, I guess no one else wants to guess. That's fine. Um, so remember that like if we look at this square, you can only move 1 or 2 squares to the right, both of which like land in a winning position. So you're basically forced to give your opponent a win if you land here. So this is a loss. Compared to this one where like you can move into the loss, right? So you can give your opponent a loss, so it's a win. Okay, now let's look at the row underneath and try see. Oh, you know what? Do you guys want to like try like fill out this row down here? Yeah, I'll give you guys a bit of time to think about like what um the win-loss states of the second row must be. Okay, wait, Jackie here has a good question, right? Well, no, I get a good query. It's like it's a bit confusing because okay, so she's asking why wouldn't this entire row just be losses because you can move to this like because you can move to this like W up here, right? This win. Um, the reason is because like just because you can move to a winning position doesn't mean you should, right? In fact, you actually shouldn't. So, for example, like this square right here, you could move to a win or a loss, but you would just opt to move to the loss, obviously, right? So that's why we're not really like worried about if you can move to a winning position or not. Like, I don't really care about that. That's why we phrase this in terms of a losing position. It's if you can give them a losing position or if you can't give them a losing position, right? like if you can give them a winning position, that's not as important because we don't really care about giving them a winning position. We care about giving them a losing position. Okay, cool. So yeah, Jackie got the right like the right answer for the second row. Um, does anyone want to like just give like okay, what do we think this square should be? The one that I'm like highlighting. Yeah, okay, I know Jackie knows, but like anyone else, it's a 50-50 chance. This one's like, come on, guys. Oh, yeah, yeah, it is. Okay, that's cool. Yeah, it's a loss because like you can't move to the right. You can only move up. And clearly, if you're moving up, you're giving your opponent a win, right? So this was a loss. But if we just look at like consider everything else, right? I mean, you can either move to the right or you can give your opponent a win by moving like for any of these squares, you can either move to the right or you can move up and give your opponent a win, which is bad. So like if we don't want to move up and give our opponent a win, then we can only move to the right. But if we can only move to the right, that's basically just the same conditions as the top row, right? So this is still a win. This one's still a win. This one's still a loss, and then this one's still a win. And then by the same logic, I mean, you just repeat this the entire way across, right? Because like moving to the next row is never good. That's giving your opponent a win. So you always just want to keep moving right. But if you always keep moving right, then again we have the same like logic where the final column is always going to be an L, and then therefore these two are going to be W's, and therefore this one's going to be an L, therefore this one's going to be a W. So first player wins. Yeah, this means that player one wins. So this is an example of so all the previous ones we had like player two wins, but this is an example of where like player one wins. Um, I think in general it would make more sense for like a random game, like in a random game that player one wins, right? Because player one gets like more control of the situation, kind of. You know what I mean? Like in a perfect like symmetrical game like chess, you think player one has more of an advantage because they can kind of control like the state after the first position. But yeah. Um, so yeah, in this case, player one does end up winning because we see that um if the square is on the bottom left at the start, then it's a winning position. Therefore, player one has a winning position at the start and they can force a win. Um, I guess in this case, if you want to write up the strategy, it's just always keep it on columns 1, 3, and 4. Like that's the winning strategy, right? Just play one, whatever they do, they always want to keep it on play on oh no, sorry, my bad. Always keep it on columns 2 and 5. Because like yeah, you always want to keep it in a losing position for your opponent. So like I guess like if we want to play like some example game just to quickly show the strategy, like you would start off by moving it here, and then maybe your opponent moves it here, and then you just keep it on these like two L columns, right? So then you would move here, your opponent moves here, you move here, right? Your opponent moves here, you move here, your opponent moves here, you move here, and you can always do that. And since you can always keep it on the two L columns, eventually you're gonna end up moving it here, and your opponent can't make a move, and then you win. Cool. Yeah, nice strategy there. And we have problem 2 here. Oh, this one's quite a classic one as well. Which was literally exactly the same. Okay, right. I don't think it was literally exactly the same. True. So problem 2, we have two
It was
players.
basically.
Yeah, it's not exactly, it's not literally exactly the same. So two players play a game with two piles of coins, one containing N coins and the other containing M coins. So these don't have the same number of coins, right? Like maybe like 7 and 5 or like 100 and 101 or something, right? Um, So they alternate turns, and each turn a player takes at least one coin. So a positive number of coins from exactly one or two piles. So you can take like 5 coins from one pile, and or maybe like one coin from another pile, but you can't take 2 coins from one pile and one coin from the other pile in the same move. So this problem's a bit different from the other two, in that like where no, it's different from the example in that taking the last coin is good in this case, whereas in the other problem taking the last coin was bad. So now we want to determine for which values of n and m can a player who moves. So this isn't like which player wins. It's for which n and m can the player who moves second win, right? Like I guess you kind of like trying to solve like it's not a specific game, but it's more like a general game. and you're trying to solve when player two wins this general game. So yeah, I think you don't have to necessarily like use positional analysis for this game, right? Like you could just try find the strategy, which isn't terribly hard to find. But sometimes if maybe if you can't spot the strategy, right, then it's good just to look at small cases and look at who's winning under which positions and try to figure out like what the strategy is, right? I think it's much more motivated um to like just look at small cases and see which positions are winning compared to losing than actually just like straight up finding the solution and like finding the strategy without like any actual like other previous work.
Wait, Chris, are you gonna go over like the general case for numbers?
I don't know the solution for that. There's no one kind of hard. It was DA on mods. I saw. I don't look at the
No,
solution.
I swear, I think you just inducted or something. Wait, what? Hmm. No, I think it's. I guess you have to define the numbers, right? That's kind of hard. Yeah, sure.
Holy crap. I kind of just like zoomed. I have okay, never mind. My bad. Okay, wait, new laptop. I have no clue what the keys are on this.
Yeah, what model?
No, it doesn't matter. Um, yeah, okay. Wait, yeah, wait. So you're saying about general numbers? Like, I don't like. You mean like when they had like n piles? Like, I'm like K piles.
Yeah, and then the numbers are different.
Yeah, well, okay, I don't no. I thought that was very DA on mods. I thought it was kind of hard. I don't try it. Well, I thought about it a bit, like using like high dimensional vectors, but it didn't really work out.
What?
Because you can, like, I was gonna solve this using like a 2D grid, right? So I was trying to think of
Oh,
like
I
three part,
like
like you know what I mean?
order.
Okay, anyway, does anyone have any ideas on like how you can set up this problem or how you can like start thinking about this? Because it's not necessarily clear. Like the way I'm gonna do it at least is I'm gonna set it up as a grid similar to the previous problem, where you have like a two-dimensional grid where each cell of the grid represents a position. So I mean I'll just set it up like this, I guess, right? So it's like we have a number of coins on power one, right? Like that can be the rows over there, and then like yeah. So each of these like um each of these cells represents a game state, right? Like for example, this cell well like this cell over here represents the state when there's two coins on pile one and then there's two coins on pile two. Oh, well, sorry, with this one, yeah, two coins on pile one and then one coin on pile two. So I guess maybe let's take an example of like n equals like 7 and then m equals like 5 or something, right? Okay, so we start in this cell right here. This one right here where we have 7 and then 5. And if we think about what a move is actually doing, right, is you can take a certain number of coins from one pile or the other. So taking a certain number of coins from like pile one means you're decreasing the value this way, right? So it means you can like move this X or like move the position of the game somewhere along this row. But if you take some number of coins from pile two, that means you're decreasing this number, and that's equivalent to moving this like X or moving where we currently are, like the current game state, somewhere further up this column. So you can almost think of it as having like a token in starting in this bottom right cell. And every move, one of them can move it like one player can move this token like a rook, some number of squares along either a column or a row. And then you want to be the one to move it to 0, 0. You want to take the last point, right? So for example, like a game could look like this, right? Like move it here, move it here, move it here, move it here, and then this player wins because they moved it to 0, 0. Okay, cool. Just so I think Jackie figured out like the actual strategy, but um so like yeah, you could just try to figure out the general strategy from here. It's not super hard, but I guess we can try to have a look at like using positional analysis to deal with this problem. Actually, I guess we don't actually have that many. Okay, anyway. So, okay, like what's the okay, I'll start us off by saying that the winning, like the game state when it's 0, 0 is a loss. And it's a loss because if you are looking at a board or like a game with 0 coins in both piles, that means that your opponent just nabbed, just stole the last like coin, like the last coins, right? Wait, we said we use coins, yeah? Yeah, cool. So that means that you've lost. So what would the game state look like for all of like for like these like squares? Yeah, yeah, it'll be a win, right? And it's a win because you can just take all the coins and leave your opponent with nothing. In other words, what you can do is you can from any of these squares you can move into a losing position, the 0, 0 position, right? You can always move into here, so therefore it must be a win for you. Okay, what about okay, like I'll give you guys a bit of time since we have a bit of time to try and maybe fill out the rest of this board by ourselves. Okay, so okay, I guess I'll just ask, what does the second row, what does this row here look like in terms of W's and L's? So I remember pitching to like Dawn the idea that we needed to like make like a pingable role on the Discord for anyone who like wants to like ping for the tutorials.
Nobody joins the Discord though. Like the Discord is useless, I feel like.
Really, not because they got a lot of people in there, right? Well, I think they've got quite a few people in there. Like, do you think we
They
ping
really
them?
don't.
Nah, check on people in there. Like, well,
They
okay, there's
won't.
more than okay, wait, well, I'll tell you, there's more than 4 people in there.
Yeah, but like that's just because nobody wants to attend the lesson.
Yeah, but if you think about it, if like 2% of the people there attend, no, because I don't. Do they even know that like these tutorials are going on? Like, is there enough like?
Do they? I don't know. Wait, Chris, have you done 20? 2014 into.
Into.
Yeah, the
Into.
one with the cube root
The
and
cube.
like the
Oh, that
almost
question. No,
inner.
I was like,
Yeah.
I no, I like had the right idea, right? It's like I basically solved it, except
Did
I
you do the
forgot the fact.
substitution?
What substitution?
Wait, did you
Oh,
like
yeah. No, I know,
yeah, that
yeah, no,
one.
like d like x minus y equals like d or something.
Yeah. I'm still working on it though. Like I got the
Okay, never
substitution
mind.
and then
No,
like
I
I was
basically
like,
solved
wait,
it,
it's
except
not an
like,
insta
sorry,
side. What the
my bad.
fuck?
Okay, sorry. We're getting off topic. Okay, so anyway, since no one answered, I guess I'll just spoil it. So this position here, 1-1, is a loss because you can only move to a win or a win on either side, right? You can either go to a win up here. So therefore, these are all yeah. Therefore, these are all like W's because you can move to this L. Okay, like if you just keep looking at this, it's basically just this diagonal here where the position is NN is a loss and everything else is a W. Okay. Wow. Very cool. Okay, so what is the strategy then? The general strategy is basically just try get onto to this diagonal. Because if you get onto this diagonal, that's like handing your opponent the loss. Yeah. So the general strategy looks something like this. You just always move towards this diagonal if you're not on it already. And if you're on it, well, you kind of have to move off it. But then your opponent can move back on it. And maybe you try to move off it. But then your opponent like moves back on it. And then eventually your opponent moves back onto it, onto the square 0, 0, which means you've lost. So like to like without needing this like table, the strategy is just try is you want to always keep the two piles the same size. So if they're not the same size at the start, you make them the same size. Then whatever your opponent does to like one pile, you offset the other pile the same amount. So they're always at the same size. Eventually, like you're gonna whittle it down to 0, 0, in which case you've won. So in this case, we see that player one wins, right? Because player one can get onto the diagonal at the very start of the game. But the question is asking for which values of n and m can the player who moves second guarantee a win. So when can like player two guarantee a win? Well, if player one can move onto the diagonal at the start, they win, right? So when can they not move onto the diagonal at the start? Well, that happens whenever like they're already on the diagonal, right? So when when n equals m, player two wins, right? Because player two can do the strategy where they always stay on the diagonal. Yeah, like this diagonal over here. And I guess that's kind of what I mean by like saying you didn't need to do this positional analysis, right? Like you could have just found the strategy like right at the start if you want to, right? It's not terribly hard. But sometimes if you're not sure, then it's good just to look at which positions are winning, which positions are losing. And also this is kind of what like this kind of demonstrates what I mean when I say like player one normally has more freedom, right? Like player one can kind of choose to go on the diagonal at the start. Like in the majority of cases when n doesn't equal m. Like this is a pretty specific scenario where player two wins. Like that's what I mean when I say play one. Like they've got more power. Right? They can kind of control the state of the game a bit more because they get to start and they get to choose like the state they give the opponent. Okay, cool. I guess we can move on to like non-constructive proofs now. This is kind of like what Jay was maybe like hinting at earlier. Um, so like a non-constructive proof is something like it's a proof where you can say who wins or who doesn't win a game or who can't win a game or something about like um a strategy for either player without actually like finding a strategy. Like, I can say player one has a winning strategy, but I might not be able to detail what the winning strategy is. So like normally this is like going to be due to something to like called strategy stealing, where it's like I assume like let's assume player two has a really good strategy. Then I can kind of like play a biding move, like a waiting move, wait for player two to make their move, and then I can try steal player two strategy. So okay, I'll give an example of what I mean with this one, right? Yeah, okay, this is the example here. So we have the game of Chomp, right? I think I have a nice, visual representation of what's going on here. So you start with an n by n block of chocolate where n times n is bigger than equal to 2. So it's not a 1 by 1 square because that's a bit trivial and it's not really nice, right? So on each turn, a player picks a square, eats that square, and every square above it and to its right. So every square that's like both above it and to its right, including the squares directly above and directly to its right. Yeah. So it's like you cut off it's like you cut off like a rectangle and then just like eat everything inside that rectangle. Um and the player who eats the last square loses. So this time you don't want to lose eat the last square, right? So like a lot of the times like we kind of flip flop between like if you want to do the last move or not. In this case, you don't want to do the last move, right? You lose if you eat the last square. And the question is to show that the first player can always win. So there is some winning strategy for the first player. Okay, so the idea behind these kind of proofs is basically we're gonna assume, right? First assume that player one, like that the player one can't win. And saying that player one can't win is equivalent to saying player two has a winning strategy. Okay, so I'll just quickly draw up this chomp board. Right? I guess I don't know how big we're gonna make it. Sure, make it like okay. So we have like a 4x7 board here. So yeah, okay. I'll just explain, I guess, how it works because I feel like you kind of need an example to explain what this like strategy stealing thing is all about. So let's say that player one, like, uh, so if player two has a winning strategy, what we're saying is that whatever player one does, right? Player one can make any move, right? Maybe player one makes this move, or player one maybe makes this move, or player one makes this move. Like out of every single move that player one can make, which is like a bunch of them, player two always has a winning strategy. Like they can always send player one into another losing position. Okay, so what we do is we imagine player one making like a small waiting move, right? Right, like because player two has a winning strategy, player one doesn't really want to be player one, right? They kind of would rather be player two. So they're like, okay, what if I just make like a useless move where I'm not really doing anything, right? Let me just bite off this top right corner. And because I've bitten that off, I've kind of like done a waiting move where I haven't really moved anything at all. I mean, this game is basically the same as the original, right? The game's like the board hasn't really changed at all. And what happens now is player two must have some move that makes them win, right? Because we assume that player two has a winning strategy. Okay, let's assume that like player two makes this move. So now supposedly this is a losing position for player one. But notice that like because player one did such like a small move at the start, actually what they could have done is they could have just gone ahead and cleared off all of this by themselves in the first turn. But we assumed that this was like a winning position. Oh, what? Sorry, we assumed that this was like a losing position, right? Because player two gave this position to player one, and player two had a winning like strategy. So if this was a losing position, but sorry, getting my words in a bit of a twist here, but we have a bit of time. Let me should I just re-explain this? Talking is too hard. Jerry, can you explain this later? Okay, so
I got you. Wait, let me get my charger
this
first.
no, I got it. Let me re-explain, right? Player one starts by doing a biting move, a waiting move where they just eat the top right corner. If player two responds with any move, for example, this move right here, know that player one could have played this move outright right at the start, right? Instead of eating that small corner, they could have just eaten this entire block themselves, like right at the start. So they could have assumed like so if player two can give player one this quote unquote losing position, player one could have given player two this quote unquote losing position right at the start anyway. Right. So this can't really be losing after all. Like because if player two had some winning strategy, which involved them giving player one the strategy, well, player one could have just stolen the strategy by playing it themselves in the first round, right? Which means that they could have used player two's supposedly winning strategy and won for themselves. But this is a bit of a contradiction because we assume that player one doesn't have a winning strategy. So if player two had some kind of winning strategy, then actually player one must also have like been able to use the same strategy. Um, that's like okay, like I feel like someone probably doesn't get what I mean. So like if you don't get what I mean, could you just like we have like quite a bit of time. So like if someone doesn't really understand, maybe you could like let me know. That'd be cool.
Wait, Chris, for the into, did you sub back in y and make it a quadratic?
Oh yeah, no, yeah, you make it quadratic. Yeah, that's fine.
Yeah. Nah, and then like I got the I did it factored nicely, right? And then I didn't
Oh,
just
when
and
you
then I
got the
just didn't
discriminant,
bother to
or
do the rest. Yeah, in the discriminant. Is
yeah,
it
no, what I did is I
like
got the
I swear
discriminant.
after you get the discriminant, yeah, yeah,
No, what I got, well, no, I got the
yeah.
discriminant, and it was some like dumb cubic or a quartic or something, and I forgot to check if factored because you want to
Oh,
show the square, right? But I couldn't tell, like, I couldn't show, like, I don't know how to
right.
tell the square, and I forgot like factoring was a thing, so I gave up. Look at the solution. I was like, oh wait, no, and then I saw that they like, factored. I was like, oh shit, my bad.
It was easy after you factored, right?
Yeah, yeah. It was after you factor, like, because you get a
It's
because you
just
get a square in the
yeah,
factorization, right? Yeah, and then the rest is like whatever.
yeah, yeah. It's just answer extraction, right?
Yeah, yeah, and then like you get some like, weird like algebra like
Facts.
yeah like general like polynomial solution or whatever. I was like whatever. Okay, anyway, okay. I think Jackie
Yeah,
understood. You know what? At least one person understood. That's like 1 out of 4. That's pretty good to be honest. Um. Uh. Okay. Whatever. Yeah. Maybe it'll be a bit more clear with another problem. Okay. So we've got another cameo here of Jay and Haotian. Okay. So let n be a positive integer that's like not one, right? So it's bigger than one. And d sub n, right, is the set of positive divisors of n, right? dn. So we have a game here where each turn a player like picks some element of d sub n. So something that's within the set dn and deletes it from the set, but also deletes any divisors of d that are like still in the set, right? And this time the player who moves last loses. Right? Mm, okay. So okay, I guess we can have an example here of 18, right? So if n equals 18, then our divisors of n, right, are just I think everyone should know these. 1, 2, 3, 6, 9, 18. So maybe J he picks D to be 9 on the first round, right? And if he picks it to be 9, he deletes 9 and he deletes 1, 3, and 9 all at the same time. Because 1, 3, and 9 are the divisors of 9, right? And then maybe Haotian now picks 6, right? So he picks 6 and he deletes 6 and 2 because those are like the remaining divisors of 6 that remain in the set. And now Jay's forced to make the last move because Jay has to delete something. He deletes 18. And okay, look, Jay loses now, right? Because he just deleted the last set. He made the last move. So in that scenario, Haotian won. But maybe if Jay played a bit better, he could have won, right? So given optimal play, we're asking for which n does Haotian win? So maybe like try use the same strategy of like the first player kind of making like a biding move or a waiting move, I guess, where you're not like you kind of not really doing anything, so you can assume the role of player two almost, right? Like the idea is kind of like suppose player one could choose to just not play. If they could just pass their turn, if they could just not play, then they'd be playing as player two basically, right? Because player two would have to make the first move. And in that case, if player two had a winning strategy, then since player one has just turned into player two by skipping their turn, they now have the winning strategy. So sometimes when you have these games where you can make like a small waiting move, that's almost the same as skipping your turn and like turning from player one to player two.
Yo, Chris, did you do the in 3 that year, the one with the Cape Town coins?
Oh, that one. No, I had to give up on that question. Even though that was, I think that was P5, right? 2014
That
P5.
was too crazy. It was actually too crazy.
It was actually two. Yeah, it was. It
Like,
was. Although Evan Chen rated it as a combinatorics question in his table.
yeah, yeah, I hate that kid.
Yeah, it was too deep. It was too deep.
Nah, but I swear it
Mhm.
was more like algebra because when they have the algebra questions with the inequalities, and then you have to do like, and then like in the official solution they go like, oh, this estimate instantly solves the problem.
Nah, nah.
Nah, those ones,
I think it was combinatorics. Like I guess it was kind of combi in like in his ideas, right? Because
sure, it was kind of like the algorithm, right?
no, because I didn't really thought of like I don't know. Yeah, it was kind of okay, whatever. It was a bit too tricky. Like I did have the idea of like never mind. I didn't have any ideas. It was too hard. Okay, sorry. Let's get back to the problem. You know, we're gonna finish early too, because it's like the last slide. Maybe
Let's go, let's go.
maybe we should have done generalized numbers. Okay,
Maybe we can
anyway,
just like yeah,
okay, wait, actually the important thing to notice, by the way, in this question, I just want to reiterate that because because there's no draws in this game. Actually, I don't think we did a single example where there was a draw, which was unfortunate. Maybe I should have found one that had a draw. But because there's no draws in this game, like one player is guaranteed to lose. That means that either Halton has the winning strategy or Jay has the winning strategy. So if we can show that like Halton does not have a winning strategy, right? If we can show that player two does not have a winning strategy, that forces player one to have a winning strategy. So um okay, does anyone have like an idea of what maybe Jay's first move should be? Well, not what his first move should be necessarily, but if we're trying to prove that Halton doesn't have a winning strategy, right? Like we want to show that Halton never has a winning strategy. Okay, so in order to try show that Halton never has a winning strategy, what could we make Jay's first move? This quote unquote waiting move where he passes the turn. Oh, even Jackie doesn't know. We're cooked. We're cooked. Oh, it's over.
wait, I swear I
Okay,
don't remember this problem.
so what
Was
is
it
like
like
the smallest, most like minimal move that we can do, which is like basically a nothing move, I guess. Yeah, one, right? Okay. So let's say Jay, yeah, yeah. So like let's say Jay just does like the most nothing move where he just does a waiting move where he just deletes one. Now Houghton has to make some move, right? So he could let's say delete like six, which deletes three and two along with six, right? But because Jay made like a nothing waiting move at the start, instead of doing that nothing waiting move, he could have deleted this at the same time, right? And in this case, he'd basically be Haltian in the previous like scenario. So whatever, if he plays one and then Haltian does like whatever to, and we're assuming Haltian has a winning strategy, then Jay could have just done what like he could have just did what Haltian did in move one, and now Jay would have the winning strategy. But that's like obviously impossible because we assume that like Halton has a winning strategy and Jay doesn't have a winning strategy, right? Which is kind of a contradiction. So again, we've shown that like if Halton has a winning strategy, then Jay can kind of just steal the winning strategy right at the start for himself and like contradict the fact that Halton's winning. Yeah. And because we said that either Jay or Halton has the winning strategy, like one of them must have a winning strategy, and we just showed it can't be Halton. That means that we've proven that Jay must have the winning strategy. Know that like the winning strategy is not necessarily picking one at the start, right? That was just to show that like Halton didn't have a winning strategy. Like I don't actually know what the winning strategy for Jay is, But if you bashed out like everything, it must be a winning strategy for Jay. Actually, this leads to like a good discussion on the game of Chomp, right? So, like for the game of Chomp, if you have a one by n grid, like I mean, we've proved here that player one must always win in a game of Chomp, right? Like if you have a one by n grid, it's pretty clear that player one always wins because they can just like eat all of this right at the start and then leave the last block for player two to eat, and then player two loses. A 2x n grid is a little bit more interesting, but you can actually find an explicit strategy for this one as well, right? And I think I actually left that as an exercise in the problem handout. So maybe if you guys want to go try that, right, that's cool as well. You can find an explicit like strategy for player one to win this game as well. But for like for n equals 3, or for m equals 3, for like a 3 by, maybe for like a 3x n grid or larger, like we don't actually know of like the winning strategy. We just know that Alice or player one can always win, which is kind of cool, Like you can show that someone can win without actually like being able to win if you're playing as them. So it's like a subject of quote, like it's like a subject of like contemporary research right now. Yeah, like it's still ongoing. Maybe you guys can like have a crack at like 3 or something, right? Just have a play around. You can like this is kind of what I mean when I'm saying like with more complicated games, you can't really do like positional analysis anymore because it's like, I mean, you can do it, but you can't generalize it because it's kind of like random which positions are winning or losing. It'll be like you can find the winning and losing positions, but you might not be able to find a pattern to the winning and losing positions. Like maybe it'll be like losing, winning, winning, like whatever, right? Like, and maybe it'll just like completely random, like, and you won't be able to find a nice strategy that describes like exactly what you can do to win or lose. So that's why like winning, like sometimes positional analysis might not necessarily help, but that's why I'm also saying it helps for like simpler games where you can just describe which positions are winning and losing quite simply. Like also like my nose is kind of getting a bit like blocked right now, so like maybe I'm sounding a bit nasally,
I
sounding a bit
got
like
you. I'll
Jerry.
yap. You're a hater. Wait.
Wait, that's my bad, my bad. That's because
Like,
you said it before. You said you sounded nasally before, like, and it was like an insecurity.
yeah, I
So
did.
like I made it
Because
into a
I did.
joke, but that was like a really messed up
Oh,
joke.
for the devices problem, uh, I kind of remember a variation of the problem where instead of going upwards from the bottom, I think it was like you had some large number. It might have been 2022 because that was the year of the
Hmm.
competition. And then instead of going upwards, you went downwards from 2022 and did something with the devices. And I think in that problem, the solution was that you controlled whether or not you had 6. So no matter if 6 was a winning position or a losing position, you could choose to like either take it for yourself or give it to the other player. And that was the strategy, which is sort of similar to this one.
Crazy stuff. All right, do we want to like end the
Crazy
lesson
stuff.
early, or do we want to keep going through more problems?
Yeah, let's
Should
end
we
it.
end it? No,
For four
we gotta ask the
people,
students,
for
bro.
four people,
Hold a
let's
vote,
end.
hold a poll.
Oh, they're
Yo,
not gonna
guys,
reply.
they are gonna reply. Okay, Jackie doesn't mind.
No,
Guys, do you want to go through more problems or like, you know?
well, the votes 1-1 since I do mind. Like, are the other students saying anything?
Nah, come on, guys. Do you guys want to keep going? Okay, someone else
No,
doesn't mind. No one cares.
oh, it's all, yeah. If no one cares, then it's 1-0.
No, you don't get a choice.
What do you mean? They're not paying me a living wage, not even minimum wage. I don't think
Okay.
we get
One
dinner
wait,
here.
one anonymous student has anonymously said they want to do questions.
No. Do we have questions from
Yeah,
the
we do have
handout or
in
something?
the handout. Wait, unless you want to make up some questions right now, that'd be cool as well.
Yeah, let's go. I'll go get the C4 from 2015.
The C4, you stupid.
Okay. Just take the handout questions. It's fine. They're not gonna do it on their own anyways, are they? Maybe we can just like sit
Okay,
down and have a karaoke session. I think that would be pretty crazy.
okay. Oh, wait, that's kind of good. Okay, you know what? Let's do this last question here because like probably wait. Oh, should we spoil a BMO1 question? That's kind of bad, right? Because that's like good training practice. Okay, which of these is like the worst like
Okay, then
question?
do double chess because that's a stupid question.
What is a stupid question?
No, Chris. Chris, do
Well,
double chess. Let them think about it for 8 minutes, and then we can talk about the solution.
8 minutes.
Yeah, eight
You're
minutes.
such a hater, bro.
Yo, Proctor, Proctor. Are we allowed to do that?
Dude, make them think for 8 minutes straight.
8 minutes. It's good practice because on the NZO2 you have to think for 3 whole hours. Like 8 minutes is just a fraction of that time.
No, but I think they solve it in like 2 minutes, right? Or maybe not.
If somebody
Nah,
solves
nah.
it, they can just say the solution and we can go for another question because that question is kind of stupid, no?
Yeah, this stupid. Okay, fine. Don't do question 4. No, no, no. No, you know what? Like, you guys can do any of these problems, okay? You can just like, wait, say any ideas you have for any of them. It's okay.
Oh wait, let's do problem 5. That one's a good problem
Is
because
that a
I
really good
remember
one
the
though? It's not really
solution.
that good.
I don't
I don't really
remember
like
the
it.
solution to any of the other problems. Like,
Hmm?
which ones are we supposed to do? No, we can't do any of the other problems because I don't remember their solutions.
You
So
can
like the
solve
only
it. It's not
choices
that hard. If you can't solve it on the spot, you're actually like washed as hell. God.
it's too deep. It's too deep.
No, problem one is so okay. Problem one is so stupid. Okay, problem one's not even a combinatorial game. You know, I'm gonna go over problem one real quick, just because it's not actually a combinatorial game.
Oh,
Um. Okay, so problem one is kind of like an example of a question where like I say winning strategy here, right? So the question is kind of like this, right? You start off with
oh,
I'm gonna
yeah, that's stupid.
yeah, I'm gonna like decrease the size of the chocolate bar. Okay, it was like what did I say? I said it was 100 by 100. It doesn't really matter, right? I'm gonna make it okay. It's a 4 by 8 chocolate bar now, right? So what you can do is you one player like each player takes turns like splitting the chocolate bar. So maybe I split it like this, and then now it's become like two 4 by 4 pieces, right? And then maybe on the next turn, like I can make a discard down here, and then now it's 3 pieces. What are you doing? Is that a ruler?
What?
Are you like slapping a ruler? What
Oh, I think it's by speaker thing on
the
the
hell? Okay, so
small.
maybe you cut it like this, and now you have like 2 pieces or 3 pieces like this, right? Um, and you keep going until like you keep like splitting these pieces until like you can't split them anymore. In which case, like they've been dissected into 1 by 1 sections, right? So you have 32 of them at the end, right? Like, and then the player who can't make a move, who isn't able to make a move at the end, they lose. So we're asking here who has the winning strategy. I'm saying it's a dumb question. I just put it in there because I was like running out of questions to put in, But it's dumb because there's no strategy. As in, like one player is always guaranteed to win no matter how you play the game. The way you can look at this question is notice like the wording here, right? Literally, a player chooses one block and turns it into 2 blocks. So like every turn you're just adding like you're increasing the number of blocks by 1, right? So at the start you have 1 block of chocolate, but after one move you have 2 blocks of chocolate, right? And after 2 moves you have 3 blocks of chocolate. So eventually, you'll have 32 blocks of chocolate, in which case, you can't make any more moves, right? So, so player one, I guess the way you can look at it is that on player one's turn, there's always gonna be an odd number of chocolate blocks, and on player two's turn, there'll always be an even number of blocks of chocolate. So at the end, since it's even, we see that this is player two's turn. Therefore, player two is the one who can't make a move, and player two loses. But yeah, there's no strategy. The strategy is literally just keep cutting it up, and both players just keep cutting it up. And no matter what they do, player two is just destined to lose. It's a pretty stupid game because player two can't do anything, and player one can't do anything either. Um, yeah, so that wasn't really a combinatorial game, but that's more like a monovariant question that like disguised as a combinatorial game. My bad for sneaking that one in, guys.
Yep, let's make them do problem 4 for
Okay, you know
2
what?
more
Problem
minutes.
4. Okay, fine. We'll make them do problem 4. I hope everyone here knows how to play chess, because if you don't, actually, I feel like maybe not everyone here. Wait, actually, it's like a small sample size, so there's a good chance that everyone here does know. Okay, Jay, do you want to drop the game board with the pieces?
Are you kidding? You do not need the pieces.
Wait, but
I'll
like
draw it.
it's literally a game of chess though. No, wait, I got it. No, you're not
What are
doing
you
anything,
doing?
bro.
No, my lines are straighter.
No, 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 get rid of your lines, bro. Literally get rid of your lines. What are your lines doing?
How am I supposed to get rid of?
Oh, okay. Jackie forgot where the pawns
Okay,
go. Don't worry, we can explain the rules of chess to like everyone first.
yeah, to pad time for the remaining 2 minutes.
Okay, let's wait, we gotta
That's
draw on
clever.
the
That's smart.
wait, what do rooks even look like now then?
Okay, I'll do the red side. You do the blue side. Okay.
Wait, no, I'm doing the black side. It's black and white, man. Come on.
How are they supposed to see white?
No,
Okay,
you just
let's do black and red, like in checkers.
there you go, bro.
Are
All
you
good.
drawing them?
Yeah, that's my nine right there. Oh god.
That's stupid.
Wait, what's the wait? No, you gotta draw them, bro. What the hell? How do you draw a nine?
Like, I think it's like, wait. No, I can't visualize it. It's over. No,
Holy.
you have to draw the nose flat. You have to give it a little air, right? Wait, I'll draw it on my side. You have to have the little air, and then it's like fat. Wait, this is just a unicorn. Yeah, that's good enough.
That's not what a bishop looks like either. Man, this is too hard. Okay. Oh, anyway, okay. No, you gotta do it properly. You gotta do it properly. So okay, wait, here's how pieces move. Pawns move up. Knights can move diagonal, like can move in the L shape. Yeah, I'm. It's 45. I quit. I quit. Yeah, it's over. I'm not getting paid overtime for this. Wait, 9 by 8. There's no way. 1, 2, 3, 4, 5, 6, 7.
What are you doing?
No, I'm not getting paid enough for this. We're ending.
Yeah, we're getting paid. Wait, tell them the solution then.
They figure out your on this. They gotta still try to figure out themselves.
Okay, wait, let's finish the chessboard, okay? Don't be a quitter.
We finished the chessboard. How do you draw a nine?
Yeah,
How do
let's
you
just end the session.
the
Proctor,
chessboard's
Proctor,
not even right.
Proctor,
It's 39 by 8.
Proctor, can we please get some assistance?
Yeah, what's up?
Yeah. How do you draw a nine?
Yeah.
Wait, guys, surely just go quickly over the solution. It's not too bad, right?
We
No,
don't
but
want to
no, we
spoil
want
the
to give
problem.
we want like
Oh,
them we
okay.
want to give them a chance to do it themselves. Wait, how do
Okay.
you draw a nine though? What is this? What is
Wait,
this?
I think it looks like this. It looks like this. It looks like
What
this.
was
It looks
that?
like this. Wait, that looks like a donkey. My bad.
No, okay, I'm not, when you just had this, okay, that looked a little bit suspicious.
Okay, what about this? What about this? No, that's an anteater. It's all